Hello everyone. Today we will start with the third unit, which is a current mirror. So in the today's discussion we will discuss about current mirrors, three important circuits about the current mirror. The first one is the simple basic current mirror, cascode current mirror, and active current mirror as a load. Okay, so today we will be discussing these three topics from the third unit. Okay, so before we start with the basic current mirror, so we will have some fundamentals of the MOS device that we have discussed so far. Okay, so this is transistor M1 and this is transistor M2. So this is NMOS device, which employs, this is source, drain and gate. This is drain, gate and source. Fine. So consider a NMOS device. We are considering two transistors here, M1 and M2. So here for the current mirror, for the basic current mirror, to act as a current source, basically any device, so it should work in a saturation region. The device should work in a saturation region. So according to that, we know that the current expression of saturation region as mu n cox W by L into VGS minus VT whole square. So this is the current expression for the device to be in the saturation region, right? So to act as a current source, so what happens to be in the saturation region? So the condition is first your VGS of the device should be greater than threshold voltage, and the second is VDS should be greater than or equal to VGS minus VT. So these are the two conditions that ensures that the device to be in the saturation region, right? So so in the entire discussion of the current mirror, what we are discussing here, it is considered that the device should be in the saturation region, right? So here, first thing, in the equation what we see here, so the device current, the saturation current ID is proportional to mu n cox W by L into VGS minus VT whole square. So here ID is proportional to the mu n cox. This mu n cox are the process conductance constant, device conductance constant it will be a constant. So ID is proportional to, first thing, ID is proportional to W by L. So these two are constant, whereas this is variable by the designer, and another point is VGS, whereas threshold voltage of the device is again constant. So your current ID is proportional to VGS. So these are the two important condition for the current mirror. Understood? And here we have another device, another condition, that ID is proportional to VDS. Okay, so if we have two device, then what happens if the W by L of both the devices are same? W by L of M1 and W by L of M2 should be same, and the current flowing through the device should directly proportional to VGS. If both the gate to source voltage, both the device gate to source voltage are same, then it is said to be mirrored. That means it's the same amount of current will be flowing through the both the devices M1 and M2. So this is VGS and this is another VGS, right? So these two conditions are important, whereas this can be different. the VDS of both the transistor M1 and M2 can be different, because of which the small change in current means it will not be exactly mirrored. Okay, for an exact current mirror, all the three conditions should be satisfied. Okay, but most of the case the third condition will not be satisfied, because of which there will be a slight change between the current flowing through M1 and M2. Okay, so whereas first two conditions are critical, that should be same in order to mirror the current, that means the current to flow through both the devices, right. So here if VGS, for example, VGS, if this VGS is equal to 1 volt, that means VG minus VS should be equal to one particular voltage, that means 1 volt. For example, this is at 1 volt and this is connected to ground. For example, VGS is 1 volt. If source is at if source is at 1 volt and gate is at 2 volt, then VGS will be VG minus VS will be 2 minus 1, VGS is 1 volt, again it is 1 volt. So the difference between the gate and the source is what I am mentioning here. The difference between gate and source should be same for both the transistor. That is the important condition here. Okay, this is the first fundamental things to be analyzed, or these are the conditions to be satisfied in order to ensure that the current is same in both the transistor M1 and M2. Okay, so here to summarize, the two transistor M1 and M2 will carry the same current if both the device has same W by L, M1 and M2 should have the same W by L, and VGS of both the devices M1 and M2 should be same. These two are critical condition. Whereas the third condition, VDS of both M1 and M2 should be same, but if the VDS is not same, the current will be different. Okay, so this is the point to understand. Okay, so now coming to the simple current mirror circuit. So simple current mirror circuit. So this is transistor M1 and this is gate, source and drain. Okay, this is VDD, and we assume another transistor over here, both are NMOS device, another transistor here, and here this is M2. So these are the two devices. So here you consider that W by L of both the transistor will be same. Okay. So for example, both will be having a 10 micrometer of width by 1 micrometer of length. Both 10 by 1 micrometer. W by L of both the devices are same, and the threshold voltage of both the devices are same again. Say for example 0.5 volt. VTH of both the devices are same, 0.5 volts. Okay. So here for for the transistor M2, consider a transistor M2. So here if I apply a VGS of 1 volt, VGS of 1 volt. So the gate is connected to 1 and the source is connected to ground. If I apply a VGS of 1 volt, say there is a current flowing through the device which is, for example, 1 milliamps. 1 milliamps of current is flowing. If I apply a current of if I apply a voltage VGS of 1 volt. Okay, I will be getting a current flowing through the transistor M2 to be 1 milliamp. Okay, so that is what we do in the transistor M2. Okay, so now consider transistor M1. So here we are doing an inverse operation. Okay, so what we are doing here, we are applying a current of 1 milliamp. Okay, so this is a diode connected MOSFET. This is the important point to note here. If I apply a 1 milliamps of current, then what happens? The VGS is itself adjusted to, okay, so the VGS is itself adjusted to 1 volt. Okay, so here what I am giving, so here I am applying 1 milliamps or 1 milliamps of current, DC current, and VGS is adjusted itself to 1 volt because of this feedback. Understood the point? So because of this feedback configuration from gate to drain, so it will adjust itself so that VGS should be at the 1 volt. Okay, so this is the inverse operation what I am doing here. Understood the point? So here in the inverse operation what I am doing, I am applying the current and generating the voltage VGS, whereas in the transistor M2 I am applying the voltage and I am generating a current of 1 milliamp. Okay, so here in both the case I have considered VGS as 1 volt, because here in the first case for transistor M2 I have, for example, I have given an input voltage or VGS as 1 volt and I am getting a current of 1 milliohm, 1 milliamps of current. And for the transistor M1, since the W by L of M1 and M2 are same and the threshold voltage of M1 and M2 are same, okay, so here I am giving a DC current of 1 milliamps, okay, current source of 1 milliamps, and and by the circuit, because of the feedback itself, it is adjusting the VGS to be 1 volt. Understood? So this type of feedback what we have given here is a diode configuration, and we have discussed about this diode configuration because if we consider a current equation, ID is proportional to VGS minus VT whole square, right? In the current equation, VGS ID is proportional to VGS minus VT whole square. So if I apply VGS, so in this characteristics, if I apply VGS, how will the current vary? The current will vary by proportion of square. Okay, so it will increase parabolically like this by square. Okay, so it is somewhat kind of diode characteristics. Okay, the diode in the forward bias characteristics. Hence, this device is again considered to be as diode configuration. Understood? This is a simple configuration that we are configuring for a simple current mirror. Fine. So now coming to the current mirror circuit. Just a minute. So it is taking page, time to move to the next page. Yeah. Current mirror circuit. So the same M1, and here I am connecting the gate of M1 to the gate of M2. Okay. So again, considering the same circuit which I have discussed earlier, which means that W by L of both M1 and M2 are same, and the threshold voltage of both the devices are 5 volt, 0.5 volt, sorry. Okay. The threshold voltage of both the device M1 and M2 are 5 volt. Okay. And this M1 is diode configured. Okay. And by a current source, I am giving a current of 1 milliamp. Okay. And since I am giving a current of 1 milliamp, as per the inverse law what I have informed, this VGS will be equal to 1 volt. Okay. VGS will be equal to 1 volt. Since VGS of this transistor M1 is equal to 1 volt, the gate of M1 is connected to the gate of M2, the VGS of M2 transistor will be also equal to 1 volt. Understood the point? So here what happens, the M1 and M2 W by L of M1 and M2 are same. Okay. So this is the first condition, and what is the second condition for current mirror? So the VGS of M1 and VGS of M2 are same, which is equal to 1 volt. Okay. So the W by L of M1 and M2 are same, and VGS of M1 and M2 are same. Since these two conditions are satisfied, this current what is flowing through the transistor M1, which is 1 milliamp, will be reflected to flow through the transistor M2 the same 1 milliamps current. Understood? So the same current is flowing through the transistor M2. So this is a simple current mirror. So here what about the third condition, what is VDS? Okay. So here in this case the VDS, it depends, it may be same or may not be same. In this case, if you consider the gate is at 1 volt and source is connected to ground, and gate of M1 is connected to the drain of M1. So the VDS is also 1 volt because the drain is at 1 volt, which is connected to the gate, which is 1 volt, and source is connected to ground, hence VDS is also 1 volt. So here the drain may or may not be at the same voltage, but it depends upon the load that I have connected over here. Understood the point? That depends upon the load that I have connected over here. So if I have a load of, say for example, 0.5 kilo ohm, 0.5 kilo ohm. So what is the drop across this load? So 0.5 into 1 milliamp, it is 0.5 volt. The drop across this 0.5 k is 0.5 kilo into 1 milli, which is equal to 0.5 volt. Okay. So for example, if this VDD is for example 2 volt, so the drain and gate are at same potential for the transistor M1, so VDS is 1. So whereas here the 2 minus 2 volts is equal to 0.5 minus VDS. So VDS is equal to 1.5 volts for the transistor M2. Okay. So VDD for both the terminal, for example say 2 volts, then VDS of M1 is 1 volt and VDS of M2 is 1.5 volt. You see the load here 0.5 kilovolts what I have added as a load for the second transistor M2 makes the drain potential, the VDS of the second transistor to be different, which is 1.5 volts. In this case, what happens? The current flowing through the transistor M1 and the current flowing through the transistor M2 will not be matched. Okay, but again at the same point, it is not that large difference also. Okay, it is not a large difference, but it is not exactly matched. The I1 which is corresponding to M1 and I2 corresponding to M2 will not be matched in this case. Okay, in order to have an exact current mirror, I need to match the VDS of M1 to be same as VDS of M2. Understood? So this is the important point to understand here in case of current mirror circuit. So this, the third condition, VDS should also be matched. So in order to match that, we come across the cascode current mirrors. In order to match that, we come across cascode current mirror. So here, for example, consider a transistor M1 in which the source terminal is connected to a current source. Okay. So here a transistor M1 having a source terminal connected to a current source which is having a current source of 1 milliamps here again. Okay, and consider the W by L of M1 is same as we have discussed earlier, and VTH is also same as 0.5 volts. Okay, understood? So here what happens? I need to get VGS to be 1 volt. This is the condition in order to have 1 milliamps of current flowing through the transistor M1. Okay. So here VGS should be 1 volt in order to have 1 milliamps of current. So for example, if gate terminal is at 3 volt, what happens? Then source will be at 2 volt. Understood? Or if gate voltage is at 2 volt, then source terminal is at 1 volt. So that your VGS should boils down to 1 volt always. Understood? So here I force the current to flow through an current of 1 milliamp, and because of which I am forcing VGS will be adjusted automatically here in this case to be 1 volt. Okay. So here this is the condition for the cascode. We will complete the circuit, cascode circuit here. This is the actual cascode circuit. Okay. So consider transistor M1, M2, M3 and M4. Right. So here in the cascode current mirror, assume that all M1, M2, M3 and M4 are having a same W by L and same threshold voltage of 0.5 volts. Okay. In the cascode circuit, we have 4 transistors M1, M2, M3 and M4, and all the 4 transistors have the same W by L and the threshold voltages are same. and I am connecting the gate voltage of M2 and M4 and gate voltage of M1 and M3, and another point to note that I am making the diode connected for both M1 and M2. Okay. So now consider transistor M2. So what happens to the transistor M2? Since the current 1 milliamps is flowing through this M1 and M2, so what will be the gate to source voltage of M2? The gate to source voltage of M2 will be 1 volt. So here current I, which is 1 milliamps flowing through the transistor M2, and hence because of the feedback you have adjusting, it is adjusted that VGS of M2 to be 1 volt. If VGS of M2 is 1 volt, that is gate is at 1 volt, okay, and source is at ground, and the drain of M2 is also at 1 volt. The drain terminal of M2 is also at 1 volt because gate and drain are shorted. So now consider M1. When you consider M1, what is the current flowing through the M1? It is again the same 1 milliamp. Okay, since 1 milliamps is flowing through the transistor M1 and it has the same W by L and threshold voltage, the VGS should be adjusted to 1 volt. VGS of M1 should be also adjusted to 1 volt. Understood the point? Which means the source of M1 is at 1 volt. So obviously the gate of M1 will be at 2 volt. Okay. So for M1, VGS, which is VG minus Vs, the gate voltage will be at 2 volt and source voltage is at 1 volt, which is connected to the drain of M2. So your VGS of M1, transistor M1 should be 1 volt because current of 1 milliamps flowing through that. Okay. So now consider transistor M4. So since VGS of M2 is 1 volt, the VGS of M4 will also be 1 volt, and the same current, what is the same current? 1 milliamp of current will be flowing through the M4. Understood? So here the gate voltage of M4 is 1 volt and the drain voltage that depends. Okay, the drain voltage depends. So here what happens? The drain voltage, the gate voltage, now this is for M4 what I have considered. As I told, the drain voltage of M4 depends. Now come back to the transistor M3. Okay, since the gate voltage of M3 is 2 volt, the drain voltage, sorry, the source voltage of M3 should be 1 volt because the W by L of M3 and M1, M2, M4 are same and the threshold voltage is also same, and it is the same 1 milliamps of current flowing through the transistor M3. So your VGS of M3 should be 1 volt. Okay. To adjust this VGS of M3 to be 1 volt, your gate voltage is anyhow at 2 volt. So the drain voltage will be adjusted to 1 volt. Understood the point? This is the important point to analyze here in the cascode circuit. Okay. So by this discussion, you see the VDS of M2 is 1 volt, that is drain is at 1 volt and source is at grounded, and VDS of M4 is also 1 volt. The drain is at 1 volt and the source is connected to ground for the transistor M4. Understood? So the M2 and M4, understood the point here? The transistor M2 and M4 act as a base current mirror, because here W by L are same, W by L ratio of M2 and M4 are same, VGS of M2 and M4 are same, and also VDS of M2 and M4 are same. So this acts as the base current mirror. Okay, and the upper transistors M1 and M3, so the upper transistor M1 and M3 acts as a cascode device. The upper transistor M1 and M3 acts as a cascode device, and the lower transistor M2 and M4 acts as a base current mirror. Okay. So here coming to the cascode device M3, what about the VDS of M3? Is it same as the VDS of M1? Again that depends. Okay, that depends upon the load that I connected to the right hand side, that is for the M3 circuit. Understood? So this is the cascode current mirror. Okay. So here in the base current mirror, what is the base current mirror? The transistor M2 and M4 acts as a base current mirror because all the three conditions are satisfied. W by L are same, VGS are same, and VDS are same. It is an exact current mirror. Whereas M1 and M3, we cannot say that, because anyhow the W by L of M1 and M3 are same and VGS of M1 and M3 are same, but the VDS of M1 and M3, it depends upon the load that we connect to the cascode device or the transistor M3. Okay. So here the current in the current mirror are decided by the base current, base transistor I mean. Okay. The current in the current mirror are decided by the base transistor, not by the cascode device. Okay. It is decided by the base current mirror, not by the cascode device. Okay. So the use of this cascode device is to make VDS of M2 and M4, which means the VDS of the base current mirror to be same. Understood? So this is the cascode current mirror. You need to understand here, we are trying to make the VDS of current mirror, which means the VDS of base current mirror device M2 and M4 to be same. Once these three conditions are satisfied, we can ensure that it is an exact current mirror. Okay. Whereas the upper part of transistor M1 and M3 acts as a cascode device or as a load for your base current mirror. Understood? So this is about cascode current mirror. So in the again cascode current mirror, we have different types of configuration, one of which is the wide swing cascode current mirror. Okay. So here we have same transistor, I mean 4 transistor M1, M2, M3 and M4, and gate of base current mirror and cascode devices are same. Okay. So here in the upper side what we do, we bias it externally, we bias the transistor M1 and M3 externally by giving an external voltage, say for example 1.5 volt. Okay. We are biasing the transistor M1 and M3 externally, and in the wide swing what happens, the drain of M1 is connected to the gate of M2. Okay, the drain of M1 is connected to the M1 is connected to the gate of M2. This is wide swing. Okay, so here again coming to the same point, current source 1 milliamp. So the same, all the transistor M1, M2, M3 and M4 have the same W by L and same threshold voltage of 0.5 volts. Okay, understood? So here what happens, current mirror to act, consider this base current mirror, that is M2 first. So consider M2. So here for the current of 1 milliamp to flow through the M2, what should be the VGS value? VGS value should be 1 volt. So this VGS, this source is connected to ground for M2. So this VGS value should be equal to 1 volt, so that 1 milliamp of current flowing through the transistor M2. Okay, and again considering the same current 1 milliamp is flowing through the transistor M1, for transistor M1 to have a same current of 1 milliamp, what should be the VGS of M1? That should also 1 volt. Okay, that should also be 1 volt. So since the gate of M1 is connected to 1.5 volt, okay, the gate of M1 is connected to 1.5 volt. So here VGS should be equal to 1 volt. So your source terminal should be equal to, will be equal to 0.5 volt. Okay, to adjust this VGS to 1 volt, what happens, the source will accumulate at 1 volt, 0.5 volt. Since the source of M1 and the drain of M2 are shorted, so the source of M1 and drain of M2, which is this node, will be adjusted to 0.5 volts. Note that. Okay, so by this what happens, the VDS of M2, the VDS of M2 will be equal to 0.5 volt. Okay, so here since VDS of this is equal to 0.5 volt, the VDS of M4, the VDS of M4 will also be equal to 0.5 volt. Okay, since anyhow M2 and M4 has the gate to be shorted, obviously the VGS of both will be equal to 1, and as per our assumption initially, all the transistors have the same W by L value. So this M2 and M4 will act as a base current mirror again, satisfying all the three conditions, that is W by L are same, VGS are same, and VDS is also same for M2 and M4, the base current mirror. Okay, whereas in the earlier case, what happens? In the earlier case, so the VDS is 1 volt and VDS of this is 1 volt. Okay. So if there is a no load at here, the VDS of this will be also at 1 volt if it is an exact current mirror. Okay. This VDS will also be at 1 volt. Okay. And what happens here? Here, if there is no load for M3 again, the VDS will be also 0.5 volt. So the voltage swing from here to here will be 0.5 plus 0.5, it is 1 volt. Whereas in the earlier case, this had, the VDS of this from here to here, this has 1 volt and this also will had 1 volt. Okay, you see here. So the VDS of this is also 1 volt and this is also 1 volt. So the peak to peak, the swing here is 2 volt in this case, whereas in the wide swing you have 1 volt. Okay, so the swing is different in this case. So this is about the wide swing cascode current mirror. Okay. So coming to the next topic, which is active current mirror acting as a load. The active current mirror acting as a load here. So I'll draw the circuit of active current mirror first. So this M1 and M2 are NMOS transistor and M3 and M4 are PMOS transistor. M3 and M4 are PMOS transistor here. So M1 and M2 are NMOS transistor and here another M5 is also NMOS transistor, which we are biasing it externally. Okay. So to get a single ended output here, so we are using a single ended output. So this is the V out. Okay. So here this M3 and M4 is acting as a current mirror. So this configuration is using as a current mirror. We are using the PMOS device and the gate of M3 and the drain of M3 are shorted. The gate and drain of M3 are shorted. So here in this circuit, the current mirror, which is P type current mirror, is acting as a, is used as a active load. Okay. So we are using this M3 and M4 is acting as a current mirror. So and it is P type of current mirror acting as a load, and this M1 and M2 we are giving two different input and we are getting a single ended output using current mirror as a load. Okay. So here this is to get a single ended output using current mirror load. This PMOS device M3 and M4 is acting as a load. Okay, instead of using a resistor load in the earlier case what we had. Okay, so we use current mirror as a load. Okay, so that is why it is called as current mirror load. And here it is the small signal. It is the small signal uh, mm, which is getting mirrored. It is the small signal which is getting mirrored from M3 to M4 instead of large signal which we use it by making use of load resistance. Okay, large signal means it is basically a DC current, bias current. Okay, so the current mirror is the signal path. This current mirror is the signal path using this active current mirror load. Okay, so we will have another circuit over here. So so this is I bias and this is M1 and M2 are PMOS device and M3 and M4 are NMOS device. You see, this is an NMOS device. So this I am mirroring. So what I am doing here, I am using this bias transistor which I am biasing it through the DC bias. So by this VGS is fixed, and because of this VGS is fixed, so the VGS of this transistor, for example M7, is also fixed. The VGS of M7 is fixed. So it is the constant current I bias which is flowing through the bias transistor will be flowing through the M7, and again the supply voltage for both is same. Okay, and this the current flowing through the transistor M7 or the actual circuit what I have explained earlier, the circuit, the current, this current mirror providing bias current for circuit, this circuit what I explained it earlier. Okay, and in this circuit what happens, so this bias current or this uh, current mirror is acting as load. Okay, so this is NMOS current mirror and this is PMOS current mirror. Okay, so the current flowing through M1 and M2 which I explained here, the small signal or the current, the small signal load, the small signal current what is flowing through M1 and M2 is biased through externally this bias current. Okay, so the difference between these two are, the earlier it is the PMOS active current mirror load and here it is NMOS active current mirror load. Okay, so this is about the active current mirror load, right? So this is about the active current mirror load, and you know the current flowing through the mirror or the device, you by providing a constant bias current you are actually fixing the VGS of the transistor, and by making use of mirroring circuits you can reflect that current flowing through that device into any other circuit as well. Okay. So, another point to mention here, yeah. Here in this case, to mention that, so here the W by L, the W by L of M1 and W by L of M2 are same, okay, and hence it is the same 1 milliamp of current which is flowing through the M1 and M2. Okay. So, instead if I increase the W of this M2 as 2 times of this, if I increase the W of the M2 as 2 times, so obviously the current flowing through the M2 will be the 2 times of this 1 milliamp, which will be equal to 2 milliamps. Okay. It is the 2 milliamps of current which will be flowing through the transistor M2 if I increase the size of this transistor by 2 times. Okay. So, by this scaling the transistor size, you can also scale the current flowing through this transistor by the same factor. This is the another advantage of using the current mirror, so that you can scale up and scale down the current flowing through the any transistor by using this mirroring concept. This is another point which I forgot to mention here. Okay. So, this is about the current mirrors, cascode current mirror and active current mirror which is acting as a load. Okay. So, this is for today's class, and in the next class we will discuss about the Gilbert cell, which is an application of this current mirror. Okay. Thank you.